Hello, my name is Hannah Fowler, and I am here with Ducking Engineering to present the Critical Design Report for the Tarleton Engineering Office Suite Design. Our team consists of the following: myself, who is the geotech lead, Jonathan, the transportation lead, Blake, the water resources lead, and Noah, the environmental lead. Here is a list of our stakeholders. Today we'll be starting with the geotechnical component. The goal of this project is to design the foundation for the office suite of the new engineering building at Tarleton State University. Here is a list of the deliverables. The bearing capacity and settlement and the detailed foundation drawings are both completed. The foundation plan is done, and the cost estimate is almost complete. The Plaxis 2D model and the general notes and inspection plan will be completed soon. The design considerations are as follows. There are 3 manuals: the structural load and the bearing capacity of the soil. The structural information that we have was provided by K16 Consulting. Here is a list of the maximum loads that we were given and the structural layout of the columns. For the preliminary foundation design, 2 foundations were considered: pile foundation and a shallow foundation. Here's the formulas used for the pile foundation to find the allowable load. The red boxes show the numbers that we used for the calculations, and because the bedrock of the ground is limestone, so we chose the lowest values to use for the calculations and assumed that it was an end-bearing pile. Here is the results of the calculations with an allowable load of 1,527 kips. The shallow foundation initial calculations resulted in an allowable load of 8,850 kips. Between the 2 of these, the deep foundation would have a much larger cost and more equipment is needed, when the shallow foundation is capable of handling the loads needed and is more economical, more cost-effective, and needs less material. So the foundation used will be a shallow foundation. Following is the shallow foundation detailed design. Here is the calculations. The foundation to be 5 feet in both directions and 1 foot deep. That gave us a factor of safety of 4.3, which is greater than 3, so it was sufficient. Next, we checked for the settlement. The total settlement was 0.823 inches, which is less than 1, so the settlement was okay. Here are the design drawings. The square foundation is 5 feet on both sides and has a thickness of 1 foot, and the foundation is 2 feet deep. The column dimensions provided by the engineers at K16 Consulting was a circular column with a diameter of 3 feet, so that's shown in the picture as well. Here is a breakdown of the cost estimate. There, the subtasks are separated, and the unit cost for each subtask, along with its coordinating number from the cost manual, is shown, and the final cost will be about $3,600 plus whatever the weight of steel is times 1,900. Because of a lack of time, I have not yet done the steel design for the concrete footings, but that will be done shortly. Using the footings, there are 2 options that are being considered: a traditional concrete mix and a recycled aggregate mix. The cost between the 2 will not be much different, and they'll all have the same dimensions. The only thing that'll change is what's used for the concrete mix. The advantages and the obstacles to using a recycled concrete mix are listed below. Some of the advantages are minimizing the use of resources and supporting local economic diversity and reducing pollution from using old materials. And some barriers include the clients not wanting to use recycled aggregate due to the lack of implementation, or the site needing a stronger footing than what recycled aggregate can provide. So all of these will be taken into consideration when deciding between the traditional mix and the recycled aggregate mix. Here's the geotechnical component, and I will now hand it over to Jonathan to talk about the transportation component. Thank you.
Hi, my name is Jonathan Mink, and I will be talking about the transportation component portion of the project. The design objective is to design a new parking lot for the new engineering building at Tarleton State University. The deliverables of this project will be a pavement thickness for the new parking lot, along with a joint and steel design. There will also be detailed drawings showing what the parking lot will look like, and a concrete mix will be designed along with a cost estimation for the parking lot. The design considerations will accommodate about 45 total parking spots with 2 handicap parking spots at the closest to the new engineering building. There'll be a 6-inch curb that runs around the length of the parking lot that will help manage the storm water runoff, along with the parking lot also having a 2% slope. The total area is just a little bit over 26,000 square feet, and it'll have a 4-foot sidewalk running closest to the length of the new engineering building. There'll also be 2 semicircles in the middle of the parking lot on opposite ends. It'll help provide a green, sustainable design. It will reduce the cost for the parking lot, subtracting the steel and the concrete. The system design, it will be for a 20-year thickness of 5 inches, and it'll have 12.5-foot spacing. The area of distributed steel reinforcement is shown here in the table. Along with the area of a little over 26,000 square feet, it will require 389 yards of concrete to finish. An air and train concrete will be used per manufacturer specifications with 15 fluid ounces per 1 ounce of air per 100 pounds of cement. For 1 yard of batch ingredient is shown as the table at the bottom of the slide, where it's shown in pounds and ounces of how much material will be needed per yard of concrete. The parking lot cost came in at just a little under $100,000. It'll include the concrete, forming, steel, labor, everything shown in the table below. The design of the parking lot aerial view is shown here, where you can see both the semicircles on each side, along with where the handicap and the ramp parking spots will be, and the entrance also. This is the design for the steel reinforcement at 12.5-foot spacing and 1/2 inch by 24-inch tie bar size. The curb cutout design is also shown here in the drawing to the right, and to the left is the saw cut and pre-mold insert steel, along with the small dowel cutout for the concrete parking lot itself. The timeline will be determined at a later date, and I'll be handing it off to Blake Denho to talk about the water resources part of our project. Thank you.
Thanks, Johnny. I'm Blake, the water resources lead. This component of the project is tasked with designing a runoff management system to convey runoff from the proposed development. An alternative design will consider best management practices to treat and contain stormwater on the site. At this stage, the proposed management system has been laid out and its components have been sized. An LID design alternative has been established that contains low-cost green components. Material calculations for the first alternative have been compiled and cost estimations are currently underway. The stormwater management system followed the design standards of TxDOT's hydraulic design manual, whereas the green infrastructure alternative followed that of Harris County's LID manual. This proposed development features a parking lot, office suite, and sidewalks. These together comprise of about 1/3 of the total site surface being that of impermeable. This is a design consideration that we must handle. The site was partitioned into parcels in order to better quantify the peak flows impacting the design's components. The design consists of a curb inlet to handle runoff from the parking lot and its respective parcel, as well as graded inlets for the rest of the site. The system directs these flows downstream through conduits into the existing stormwater line under Lillian Avenue. An earthen berm partitions the parcels. Slots are placed around the curb inlet to convey any carryover discharge from parcel 1 for further capture downhill. The methodology used in this design's development involved the calculation of peak flows through the rational method with data from NOAA Atlas 14. Both the curb and graded inlets were sized with equations provided by TxDOT. The conduits were sized through the application of Manning's equation. To ensure that the flow velocity fell within the pipe's specified range, the slopes were again established with Manning's equation. Prefabricated components with these parameters were selected for ease of construction and low cost. It was calculated that a 19-foot long curb inlet would be needed to capture all of the runoff of parcel 1. However, the carryover discharge associated with the 10-foot long inlet was found to be within TxDOT specification, and a prefabricated inlet was selected. The smallest commercially available graded inlets were calculated to be sufficient as well in all 4 locations they exist. The smallest commercially available concrete pipe was also found to be adequate. Mirroring that of the land surface, a 2% slope was calculated to meet the minimum and maximum velocity constraints. The LID alternatives components were selected for based upon their ease of implementation, minimization of cost, and maintenance, as their size will be sized so that they can capture the first inch of runoff as specified. Its management train directs runoff from impermeable surfaces to detention components which allow for water quality treatment and detention. A cost estimate for the designs will consider materials, excavation, pipe installation, labor, maintenance, and additional grading. The upcoming tasks with this project component include life cycle analysis, a risk and uncertainty analysis, and finalization and specifications of cost estimates. Thank you. I'll hand off to Noah.
Hi, my name is Noah Eason, and I'm the environmental lead for this project. So Tarleton State University has been recommended to reduce their lead concentration levels from 800 milligrams per kilogram to below 400 milligrams per kilogram before any further construction can begin on the office suite. Deliverables to be included are the design criteria, design schematics, preliminary lab results, and cost estimations. So we know from the Phase 1 site assessment that the construction site was near a former lead smeltering factory that had been demolished and inactive for multiple years prior. And evidence showed that these fine-sized particles were released directly into the air and were carried to the site by wind and rain. And based on the soil boring logs, we can see that the soil does not become saturated until 21 feet in depth, which means most in situ processes can't be done without having to completely saturate the soil with an electrolyte and chemical solution that can be very detrimental to the environment. From there, that's why we recommend for you to do an XC2 electrochemical remediation, which involves excavating the soil, transporting it to our remediation site where we can pre-treat it with a KCl and acetic acid solution, and then send it through our agitator table where the lead can be collected, run through a water wash, and then sent to a landfill. And from there, the soil will be collected from the agitator table and transported to our electrokinetic reactor to get another portion of the lead out, and then that portion will be sent to the landfill, and then the soil can be sent back to the construction site to be mixed and compacted. So based on some of the soil that we got from our soil borings, we were able to run a test with a 5% acetic acid and KCl solution at different pulp densities and achieve a highest average percentage of 58.5% with just a soil wash. And from there, we took that same soil and we ran it through a small batch on our electrochemical reactor and ran it for a high of 30 minutes, which we were able to produce a 97.3% reduction in total. And for remedial option number 2 is almost the same as number 1, except we'll be omitting the electrokinetic process and just doing a soil wash, of which would be done the same way as excavating the soil, transporting to the remediation site, and pre-treating it with KCl and acetic acid, which will then be run through the agitator table, in which lead will be collected, washed with distilled water, and sent to a landfill. And then that soil will be sent back to the construction site to be mixed and compacted. As we saw before, the 5% acetic acid and KCl solution yielded the best percentage at 58.5% on average. And up next, we're going to go through the cost estimates of both of these designs. So the cost estimate for the electrochemical design comes out to be almost $3.4 million, of which the electrokinetic process and soil washing process are charged at a per cubic yard basis. And both of these include cost of electricity, cost of labor, and the actual design for this process. Then the cost estimate for just the soil wash run is at a little over $1.9 million, and is the same as the one before, except we will be omitting the electrokinetic process. So from there, Decking Engineering recommends that Tarleton State proceed with option 1 of the remedial action plan, as it has the highest chance of success with reduction of lead levels below 400 milligrams per kilogram, with a 97.3% reduction compared to the 58.5% reduction. It should be noted that these are laboratory results, and you are expected to yield a certain percentage of error when applying to a much larger quantity of soil in a real-life situation, which puts option 2 at the risk of not achieving the 50% reduction recommended by TCEQ and the EPA. This is the environmental component timeline. These are our references. I want to thank you for coming out today to listening to our process for you. If you have any questions, comments, please let us know. We look forward to answering them